Hello, students. So we've already used functions uh, in functions. We've used some built-in functions like sum in order to create functions that we've already made. But we haven't used any functions that we've made in functions that we've made. So let's try to think about some examples where we might want to do that. For instance, let's say I wanted to know the sum of the divisors of a number or the number of divisors of a number. Well, in order to do that, it would be helpful to first have the divisors of a number. Okay, so let's make a function divisors. That's going to give me the divisors of the number n. And we've already looked at divisors before, looked to see what divides what. But how would we do this? Well, first I have to decide how I want it to return the divisors, right? Do I need the extra structure of a list? Well, a list will keep things in the same order no matter what, but I don't really know if we need that here. So let's just try and make it a set. Okay, so now I have to look at where we're going to go to in order to get the divisors. Now, what's the smallest possible divisor? Well, 1. We're sticking in the positive integers here. What's the largest possible divisor? Well, n. So I'm going to need to make that n plus 1. And what numbers do I want to include in this range? Well, I only want to include the ones where if I take n and I divide it by I get a remainder of 0, because that means I goes in evenly. So let's hit enter here. Divisors of 6. 1, 2, 3, and 6 working so nicely. Now, if I wanted to, and this is really just a matter of taste, I could also do something like this, because I know that 0 returns 0 returns false. So this will work the same way, divisor 6. It's really a matter of taste. I mean, what? It saves us a single character. It's not like it's a big length thing that it's going to save us a lot of room here. So whatever you like. If you find this easy to read still, then that's fine. If you find this more confusing, then don't use it. Use this one. Okay. So now we have a divisors function. Suppose I want sum of divisors. Well, what I could do is I could have it return the sum, and then I could have it call my previous function to take the sum of the divisors. And what am I going to do here? Well, let's try the sum of the divisors of 6. That should be 6 plus 3 plus 2 plus 1, which is 6 plus 6. That worked nicely. Suppose I have 12 here. Well, now we have divisors like 4, so it's going to be bigger, but we have 1, 2, 3, 4, 6, and 12. So that should give us 28 there. So very nice. Suppose I want the number of divisors. Well, not hard either, because once we have our divisors function made, I could just say, hey, how big is this collection of divisors? So if I want to know the number of divisors of 12, that's going to be 6. And that's our 1, 2, 3, 4, 6, 12. Okay. So you could see that we can sort of chain functions together. Let's make another one. Let's say sum of proper divisors. Oh, what's a proper divisor? Well, it's a divisor of n that's less than n. So we're looking at what things like, let's say, I know that 12 divides 12, right? So you might say, okay, I want to know what are the divisors of 12 that are less than 12? That's a proper divisor. So it's like you're throwing the number out itself out of the club. Okay, so what could I do here? Well, in order to do this, I actually might want a proper divisors function. I don't necessarily need to do it because I could take it out, but you know what? Let's make a proper divisors function first. So what I could do here is I could return the set of I for I in the range. I go from 1. Now, I don't want to include n itself, so I'm going to cut it off there. Now, you might be saying, that's ridiculous to go all the way up to 1 less than the number. Because do we really have to check 99 to see if 99 divides 100, or 100 divides 101, or 101 divides 102? Aren't you being dumb here? Yes, I'm being a little dumb here, but we're keeping things simple. I mean, obviously, the worst case scenario is by halfway through, right? Because you have a situation where 100 is 50 times 2. So you get halfway through and you find the last biggest divisor that's under 100. But let's just keep this. Let's go all the way up to n minus 1 with this range. We don't need speed. And we'll say if n mod I is equal to 0. So now let's return the proper divisors of 12. And now I get 1, 2, 3, 4, and 6. Now a number is perfect if it's the sum of its proper divisors. This is a math definition. So what do I know? Well, I need the sum of the proper divisors of n has to be equal to n itself. So I can now start hunting for perfect numbers. Let's see. Let's try to find all the perfect numbers. Let's get a list of the numbers themselves. From 1 to, let's say, 99. Now, there's not a lot of them. We're going to get 2 in this range, 6 and 28. Another thing that we consider in math sometimes is abundant numbers. These are numbers where the sum of the proper divisors is bigger. Well, I can just do that. Not the nicest indentation, but it would have worked anyway. So now I can actually hunt for abundant numbers. And let's do that. Let's just change that. And now I see all the abundant numbers. These are numbers where if I sum the proper divisors, I actually get something bigger than the number itself. And you could see here with 12, if I add 6, and then I add 4, and then 3, and then 2, and then 1, that's going to be more than 12 because 4, 3, 2, and 1 are more than another 6. So you can see this is a powerful thing using functions inside functions. We can build up sort of a base of functions and just keep making functions, and we can do more and more in Python this way. Suppose we want deficient. That's the opposite of abundant. So we have abundant if it's bigger, perfect in the middle, deficient if it's less. So how could we do deficient? Well, what I could do is I could, do something with the proper divisors, but I want it to return true if it's not abundant and it's not perfect, because then it must be deficient. So I could do this. And just to emphasize, Python would parse this the way I want, but just to emphasize for the reader, it doesn't hurt to do that. And then I could ask for a list of the deficient numbers. And these are the numbers where the sum of the divisors is actually less than the number itself. As you see, we have a lot of deficient numbers. And of course, if we wanted to, we could De Morgan this as well, if you know De Morgan's rules, because if you have a not A and not B, well, we could just do not A or B. And we're going to get the same list here. So if I were to do this, and we're writing over this function, maybe not the best unless I want to remove the previous one. So, and you can see we've gotten the same list. So these are some nice examples of using functions in functions to sort of build up and do some powerful things.